Can everybody hear me? Oh, yeah, I can hear myself. All right, so all I heard from you, Mario, was embarrass my wife. Got it. Okay. Can do. It is a humbling honor and pleasure to be here. And I'm going to wander around because I don't like to just stand in one place for too long. And there's a little bit of audience participation in this as well. So if you get a microphone in your face, be prepared for it. Try to stay awake as long as you can. I'm going to talk tonight about something that's at slight angles to the theme of this convention, and that is astronomy without light. And being in this place for the first time has been really transformative for me over the last few days. And I wanted to reflect a little bit on this, and I'll come back to it at the end. And I feel that up on Breezy Hill, the seeing's fine. The Milky Way, the stars divine. At set of sun and rise of night, I see the faintest, farthest light. But what does that mean? What does it mean to see the stars and galaxies in the night sky? And to begin, we have to think about what it means to see at all. And it means to see that our eyes are sensitive to a certain part of the electromagnetic spectrum. Light is a wave. It comes in many wavelengths. And the human eye is sensitive to a very narrow range of those. And we recognize these as the familiar colors, red, orange, yellow, green, blue, indigo, violet, Roy G. Biv. But we also know as astronomers that this visible light is a small part of the grand spectrum of light waves. They can be much longer than we can see, infrared, radio. They can be much shorter than we can see, ultraviolet, X-rays, gamma rays. So already we as astronomers have a sense that there is more out there than our eyes are attuned to see on their own. And as human beings, we evolve not just biologically, but technologically. We extend our senses by building technology to see the things that our eyes cannot. And we can reflect on the beauty of the world around us. This is the only jump scare in the entire thing, I promise. Okay, we can reflect on the beauty of the world around us and the things that we can't see, but can appreciate nonetheless by thinking about the humble scorpion. And the reason I picked the scorpion is because, and I'm sure many of you know this little fact already, if you look at the scorpion under ultraviolet light, it looks completely different. There's a reaction in the atoms, in some molecule, in the shell of the scorpion that responds to ultraviolet light, and they look like this eerie, iridescent creature. They're no longer this sort of brown copper color, but this otherworldly sheen of teal. They respond to ultraviolet light. And you have to look at this and think for a second, this must have some kind of advantage or feature, or it wouldn't exist. It would be odd to have a creature whose outer skeleton is constructed of something that responds to ultraviolet light. Even biology recognizes that there is more out there than just visible light, and it's important to take advantage of that. We can look at the sun and we can have the sort of same exercise. Now, you all know, I know, you don't go out and look up at the sun and stare at it. That's the end of your staring at the sun days. That's probably the end of your staring at anything days at that point. And if you tried to do it, right, you'd be overwhelmed. Your eyes would just be completely flooded with light. It would begin to do serious damage to the structure of your eye. But again, we humans are smart. We've evolved technologically. We know how to filter this light. We know how to narrow in on features of the sun. And of course, one of the popular ways to do this is to only look at one of the very specific colors of red that comes from the sun, the hydrogen alpha or H-alpha line, a very specific narrow range of wavelength of light. And when you do this, you begin to reveal details and features of the surface of the sun. So already we can see here from this image that was taken back in 2022 that there are features on the sun. If you were today over at the Porter Telescope and had the pleasure of looking at the image of the sun there, you would see that it was a pretty busy day on the surface of the sun. Those sunspots are often as large or larger than the Earth itself. If we then get away from red light, which a human being can see, this wavelength is perfectly visible to your eye, we can look in places where the eye cannot see. So this is a wavelength of just 13.1 nanometers. This is far smaller a wavelength than your eye can perceive. So this is extreme ultraviolet. And one of the lessons we learned from physics in the 19th century is that heat and the color of light go hand in hand. And the more you heat an object, the more you get ultraviolet and very short wavelength light coming off of it. So hot things give off shorter wavelength light and more of it. And so as we look at the sun in extreme ultraviolet, we are treated to features that our eye can't normally perceive. And these are especially hot features on the surface of the sun. So now if we go from the red filter from a moment ago to here, yes, we still see the sunspots, but now we see that there are these great flares, these great hot regions here on the sun. The structure is much clearer now. Those really hot things our eyes by themselves could not have seen. And if we go even more extreme ultraviolet into soft X-rays, so we're getting into almost X-ray wavelengths here, now we're seeing the extremely hot features on the surface of the sun. These flares here are particularly intense. Some of the other structures we saw a moment ago are gone, but these are very hot structures on the surface of the sun. And it's of course then possible to piece all of this together in some way. And so we can stack images of the sun taken in various wavelength range, and we can decompose our parent star into this incredible picture of structure far beyond what our eyes on their own can perceive. This is an incredible feat that humans have accomplished. And so what we can see from this is that there's clearly more to the universe than visible light. But what we've learned over the last century is that in addition, there is a whole lot more to the universe than just light itself. So let's explore that a little bit. We can take a look at the surface of the sun again. So this is from September 10th, 2017, a particularly spectacular X8 class flare. And what you'll see around 23 seconds into this video is really one of the most stunning things. You're still seeing light in all of this. I mean, these are spectacular. These connections and disconnections of these magnetic field lines on the sun in this time-lapse video are striking. But that, right there, that moment was the moment that something other than light mattered to the story. What did you see that went by so fast? That, I captured it for you. That disruption to the imaging systems on the satellite was the harbinger of something else that the sun is also producing when these explosive flares rise off the surface of the sun. And what you're seeing here is the effect of the blast wave of the solar wind blowing through the instrument for a moment and knocking out its electronics briefly. That's the glitch in the video that you saw there, and that's what it looks like when it happens. That's not light doing that. That's something other than light. It's probably electrons, it's probably protons that are kicked off the surface of the sun, electrically charged particles that make up the atoms that make up the sun. So, this is an illustration of the solar wind, definitely not to scale, but this gives you a sense of this idea. There is space weather. The sun generates these incredible steady streams of high energy, electrically charged subatomic particles that stream through the distance between the surface of the sun and the Earth. They encounter the Earth's magnetic field. There's all these interesting interactions between this blast wave of particles and the Earth's magnetic field. But one of the key effects of this is that when these electrically charged particles encounter the magnetic field, they're primarily channeled into the magnetic polar regions of the planet. And of course, this gets quite spectacular. This is a recent photograph I took out of my backyard of a KP8+. It was more than KP8 Aurora. And I'm in the city of Sudbury, Ontario, so there's a lot of light around. I have a smelting facility lit up like a Christmas tree 24 hours a day on a hillside not terribly far away from my house. And yet, it was possible to see that the sky was dancing, and the sky doesn't normally dance. So a slightly long exposure on a modest camera phone revealed this structure of greens and blues. This is revealing the atomic structure of nitrogen and oxygen in the upper atmosphere as these things are blasted by waves of electrically charged particles that ionize them and then give off light. So light is the result in the end, but what's coming in is not light. So humans obviously need to worry about these things. You saw what this intense wave of electrically charged particles does to electronics on a monitoring satellite that's observing the sun. Our planet is now surrounded. I mean, all of us saw this. The skies here are perfect for seeing this effect. It's been a while since I've been under skies this clear, and I was struck by how many more satellites I see in the night sky than I saw 7, 8, 9 years ago, the last time I really thought to stare at the sky for a long period of time. So even I, in my lifetime, am struck by the number of artificial satellites that are now obviously in low Earth orbit around our planet. These satellites serve communications, global positioning system, and other features, scientific exploration, military applications, but they all have electronics on them, and if they get too much electrically charged particle radiation passing through them, they can blow those electronics out. So it's extremely important that these satellite owners know in advance that these particles are coming so they can power off or power down the electronics in these satellites to protect them from permanent damage. So this is one of a fleet of spacecraft that's part of real-time solar weather monitoring. This is the Discover spacecraft, or an artist's illustration of it. There's a fleet of these observatories located at the Lagrange 1 point, the L1 point between the Earth and the Sun. There'll be a cartoon of it in a moment. It's about 1 million miles away on a line straight between us and the Sun. And what this fleet of satellites does is it provides real-time solar weather monitoring information. You can go to the website here. You can look at this weather in real time. It's particularly exciting during times when we are expecting aurora, because I think this gives us about an hour's worth of warning before the aurora will flare. This is how they know that the auroras are likely to flare. We have monitoring equipment for this stuff. And you get about an hour's notice on whether or not there's going to be a really good injection of electrically charged particles into the Earth's magnetosphere. So the typical speeds of these particles is something like 600, 500 kilometers per second. At those speeds, it takes about 3-ish or 4-ish days for the solar wind particles originating in, say, a flare from the sun to make the journey from the sun to the Earth. And in comparison, the speed of light makes this jump in 8 minutes. So 3 days for these electrically charged particles. They're heavier, they're slower moving. They tend to bounce into each other and get tangled up as they move. Light doesn't really have that problem, and it has no mass. It moves really fast. It moves as fast as anything can move. And so if Discover's out here at the Lagrange 1 point and it detects an incoming increase in the number, the density, the speed, the energy of these particles, using light, you can traverse the distance between Discover and Earth much faster than the particles will make the journey. And so you can actually give warning ahead of time, and that should be sufficient warning, if anyone's listening, to turn stuff off in orbit if it needs to be switched off. So that's about protecting infrastructure. That's about predicting solar weather at the sort of observer level. This is about anticipating really interesting auroras. And there we go. Okay. But if you stop and think about it for a moment, when you think about imaging light, it seems pretty intuitive as to how you go from light to an image. Our eyes do it all the time. How do you go from something that isn't light to information or imaging about the source of the non-light stuff? So how do you make an eyeball for things other than light? And you can actually just start with the human eye and optical systems that we now know are effectively modeled on the structure of the human eye, like telescopes and microscopes and so forth. There's a set of lenses for the light that focuses and defocuses that light as required. The lenses can move and flex, they can shift. There's an iris to limit the amount of light that comes in. That light is then projected onto an imaging system at the back of the eye that then converts the light into electrical signals. Those electrical signals are transmitted to the brain, where they are then processed. If we do some Q&A at the end, if I don't burn you out, there's sort of interesting about where everyone's very excited about artificial intelligence. And it is pretty exciting. Self-driving cars, image recognition, spicy prediction of your sentences, trying to sound like a human when it's answering questions. Ask me where all that comes from, and it actually ties to the eyeball of a particular animal. So here is an example of an eyeball for something other than light. This is the Alpha Magnetic Spectrometer, or AMS-02 instrument. It is a payload attached to the International Space Station. It was the last large scientific instrument to be flown up using the space shuttle. It went up on the last space shuttle that ever flew. So it just barely made it into orbit on the ISS. In fact, there's the space shuttle right there that brought the payload to the space station. What is this instrument? This instrument is a sandwich of electronics that are sensitive to different kinds of non-light particles. So for example, non-light particles, electrons, protons, helium nuclei, I mean really anything that nature can throw at it that's electrically charged will enter in through this first set of layers, pass through this second set of layers, go through a third instrument here, and then slam into a very dense piece of material that's designed to try to stop the particles. These first layers, their job is to tell us how fast the particles are moving and what is their electric charge. Is it positive? Is it negative? So all of that instrumentation is meant to give us that information. How fast, and then what kind of charge. This last piece is designed to tell us how much energy the thing had by stopping it. And so we know how far it penetrates, we know how much it took to stop it, we can figure out the energy of the particle. This is how you make an eyeball for something other than light. And it uses some of the same principles. You need to turn light in the eyeball into something that the brain can understand. And in this case, it's electrochemical impulses. For this device, you need to turn electrically charged particles into something a human can understand by ripping out all of the key pieces of information. Where were you going? Which tells me where you came from. How fast were you going? How much energy did you have? And by the way, while you're at it, what's your electric charge? That's basically the key pieces of information we need to know to fingerprint non-light particles. So let's do some audience participation here. Let's see what some objects look like when viewed with something other than light. So I'm going to wander out here a little bit. Uh-oh, people sense I'm coming for them, right? Okay, so here you go. Ponder this for a moment while I wander in front of you. What do you think this object is? And then the second question is, how do you think it was imaged? So I'm going to go here. What do you think this object is?
I have no idea.
No wrong answers. Actually, there's lots of wrong answers. I apologize for that. I lied to you. I don't know why I lied to you just now. I feel like I could. Yeah. What do you think?
And I have a vivid imagination.
Okay. Okay. Is it child safe? It's an astronomical object. Here, we'll leave it at that. Yeah, what is that, right? What is that blurry thing? See, I've left maybe some little clues on the edges there. Could that be degrees? Could that be millimeters? What could that be? This is a lesson I always tell my students. Put units on your graphs. I took them off in this case to make this more challenging. All right, I'm going to stop torturing you. What's your name? Okay, we'll come back to that. I feel like I'm in my class again. Like, would you like to answer a physics question? Sure. What's your name? Oh, God. All right, I'm going to come over here. I think this family looks like they can be bothered. What do you think this is?
Oh, God, I have no idea.
Okay. Well, I mean, I know you have no idea, but do you have a guess?
A nebula?
Okay, a nebula. There we go. An astronomical object. Okay, nebula. Who wants to take another guess? We'll do one more. Anyone? Okay, great. We have a guess over here. Excellent.
A supernova?
Okay, a supernova. There we go. All right, you're all going to be really disappointed. It is not the sun. It's the moon. It's the moon. And how was it imaged? So the clue for the image is that there's actually word degrees, and the moon takes up like half a degree in the sky, something like that. And if you look at that blurry blob I showed you a moment ago, it has about the right size to be the moon. It could have been the sun, right? Because they're roughly the same angular size in the sky. How was it imaged? It was imaged using something called cosmic rays. So what are cosmic rays? So cosmic rays are these really high energy, electrically charged particles that are raining down on the Earth from all directions in the sky. Now, we know now that they're mostly really high energy protons, so the hearts of hydrogen atoms. And there's really good evidence that they originate in supermassive black holes that are feeding and they're belching material out in these really huge jets, these jets accelerate the particles inside of them, and a long time later, they crash into Earth's atmosphere. And because there are galaxies in every direction, there are supermassive black holes, it seems, in the center of every galaxy, these things are coming at us from all directions. The moon is in the way sometimes, however, and cosmic rays will get blocked by the moon's substance. So what you're actually seeing in that image is a shadow cast by the moon in cosmic rays. It's a place where the cosmic rays are less often occurring because they happen to be right where the moon is. And that image is a couple of decades old at this point. It was made using an experiment called Sudan-2, which my spouse will know. It was in a mine in northern Minnesota, and it was a cosmic ray observatory, and they made this really beautiful shadowgram of the moon using cosmic rays. All right, so that's what I just said there. So I've talked to you about cosmic rays already. They're raining down on the surface of the Earth. They slam into our atmosphere and they spray subatomic particles down. You're being bathed in the results of cosmic rays right now. It's a pretty common form of radiation on the surface of the Earth. In fact, a fact that I mentioned at the Hartness House workshop the other night was that one of the reasons that airline crews have to limit their flight time, total flight time in a week, is because they fly really high up in the atmosphere all the time. They're less shielded from cosmic rays. They actually get a higher dose of radiation than most other people in most other professions, including people in radiation industry like nuclear power plants and things like that. And that's just because they're constantly exposed to cosmic rays, and so that has to be monitored and limited. So this is a real problem for some of the science that I do. Cosmic rays are raining down here all the time. If you're trying to look for some rare thing with a really sensitive instrument, you are blinded constantly by cosmic rays, and you've got to find a way to filter these out. So one fun thing you can do is these programs come and go from the App Store, but I did find one last night that's currently being run out of Japan. But there's an older cosmic ray app that I used to run, and you can take your phone and you can turn it into a cosmic ray detector. And you can turn it into a cosmic ray detector by making it a really, really bad camera. So the idea is that you get yourself like a Post-it note. I went to Ace Hardware and got some Post-it notes. You get yourself some black electrical tape, got that at Ace Hardware too. You take your iPad case and you compromise it. You cover up that little hole where the camera would normally look through the case. So now the camera doesn't get any light. Well, that makes it a terrible camera, but it makes a fantastic electrically charged particle detector, because any electrically charged particle that punches now through the tape, through the paper, and through the camera sensor will then light up a pixel or multiple pixels in the CCD camera. So you are basically using the camera to take a picture of the dark, the absence of light, but if anything electrically charged punches through the sensor, it can make an image. And these cosmic ray applications will read out the CCDs all the time, look at the noise levels, subtract that off, and look for hot pixel groups that show up, including, and this is one of my favorites, lines of pixels. This is where a cosmic ray has punched horizontally through the sensor, and as it goes along, it ionizes some atoms, and then it ionizes some more atoms, and then it ionizes more atoms. This is a photograph of a cosmic ray particle passing through an iPhone camera sensor. And I love this, because this is something you can do with an iPhone in your pocket tonight if you want to. You can turn your compromised iPhone camera, which has now been covered with tape, into a cosmic ray detector. And I'm going to come back to that theme in a minute. All right, last audience participation for the evening. You, gentlemen, you work for an unnamed company. What do you think this object is? You weren't at the Hartness House workshop, were you? Oh, excellent. Okay, you get to answer this now. What do you think this is?
Oh boy, so it looks like degrees on the bottom again. So we're looking at something that's about 40 degrees by 40. Is it the heart of the Milky Way?
Is it the heart of the Milky Way? It's a poetic answer. Okay, anyone else want to take a guess at this? Heart of the Milky Way. Anyone want to top that? I like the line of reasoning on this. It's going to stab you in the back, though. Okay, all right, well, let's just get to it, right? Everyone wants the reveal. So what is this object and how is it its image? Ooh, you got to answer that question. How is it imaged? Heart of the Milky Way.
Cosmic ray density.
Okay, cosmic ray density. I like this. You're really embracing the lessons of the previous slide. So, it is the sun. Specifically, it is the core of the sun, and it was imaged using something called neutrinos, which are part of cosmic rays, but not normally the ones that you can detect with your iPhone. So what's going on here? The neutrinos are forged in the nuclear reactions, the fusion reactions at the core of the sun. They come pouring out. They make it out. Light is also made in the core of the sun. But unlike neutrinos, which can punch clean through the sun without even noticing that other atoms are there, photons get all tangled up. Photons love to interact with electric charges, and a giant ball of plasma is nothing but exposed electric charges. So those photons will rattle around after being made in fusion reactions in the core for hundreds of thousands or millions of years before they'll ever actually make it to the photosphere to then be released to be seen. So we can't actually use light to see the core of the sun because the sun is in the way. But neutrinos, they can't be bothered to interact with anything once they're created. They can pass through a light year of lead stacked end to end to end, and there's only a coin flip chance that a neutrino would be stopped by that. That's how rarely neutrinos interact once they're produced. So you can use neutrinos to see things that you can't see with light, like the core of the sun. Now, I'm sure you're wondering, wait a second, Steve. The angular scale on that was way bigger than the angular scale of the sun, and that's because neutrino telescopes don't have great pointing resolution. So that was the core of the sun, but spread out over an angular area way bigger than the sun itself. It's like a really blurry photograph of the core of the sun. And that was the deceptive part of that. Those neutrino telescopes that take these images, they're just not as good as your telescope. They don't have that kind of really good angular resolution yet. And maybe not ever, but certainly not yet. Okay, I said that already. So to see neutrinos like this from the core of the sun, you actually need an observatory that is not constantly being struck by cosmic rays. So in order to make that observatory, to make a neutrino telescope, you have to shield it from cosmic rays. And the only way to do that, practically speaking, is to go deep underground. You have to get under the surface of the Earth, just 10, 20, 30, 40 meters of rock is usually enough to stop a great deal of the cosmic rays. The deeper you go, the fewer you see. So the deeper you go, the less of a problem cosmic rays are, and the easier it is to see really rarely interacting things like the neutrino. So let's go deep underground. If you were to come to Sudbury and visit SNOLAB, you would see this surface building. This is the surface office building and laboratory space for the facility in Lively, Ontario. What you would do is you would gear up. You have to catch a 6:30 elevator in the morning to go down. That's when the shift begins. So you'd gear up in personal protective equipment, and then you'd make the walk from the surface building here. It's about a 2-minute walk through some designated walkways over to the number 9 shaft headframe. And this is this facility. This is an active nickel mine site that's operated by the Vale Base Metals Company. It's a Brazilian company. But we have a partnership, and they operate the lift facility. They provide all of the mine operations. We have to focus only on laboratory operations for our space 2 kilometers underground, so about 1.2 miles underground. So you're going to get on a cage. The cage looks like this. This is actually only half the cage. It's a double-decker. You can fit 40 people on each deck. What you do is you stand shoulder to shoulder in 4 rows. And this is the joke I cracked at the Hartness House workshop when I went over this part of it, but you really get to know your neighbor's deodorant choices for that morning. Since SNOLAB people will shower again in a moment when they get into their lab, you're not actually obliged to wear deodorant before you go in here in the morning. All right, so we pile on this cage. We share it with the miners, so there are miners on these cages too. And then we ride that cage down 1.2 miles, 6,800 feet, 4 minutes. So, yeah, I heard that from over here. It's like the effect on the body, you'll feel it in your ears. The effect on the body is very similar to getting in a jet that then pressurizes when it takes off, so a commercial airline jet. So if you have problems with your ears popping on a commercial airline jet, then the effect will be similar. When we do this, we always tell people pressure is okay. You can relieve it by chewing gum, moving your jaw, yawning, whatever you need to do. Pain is never okay. And we are very hyper aware of safety because obviously this is an industrial environment. It's a mine, and we can't do our science if we are not safe. So we ride the cage down 6,800 feet. The SNOLAB folks get off, and then they have a walk of about a mile, a little over a mile, to get to the laboratory facility itself. That's SNOLAB, and there's a little map of it here, but I'll come back to that in a moment. So here's just a little video of what it would look like, little snippets from a morning like this, where you would go underground. So you would start at the surface building, and then we're going to hop in the cage, and we're going to ride that down. So you're going to see here in a moment a very brief glimpse from the cage ride. It's like a vertical subway. Okay, that's the same. It feels like that. It sounds like a subway. It feels like a subway, but you're going up and down. Then you have the walk through the regular mine drifts with all the protection to keep rock from sloughing off. There's that mesh all the way around the mine shaft walls. Now, this is the part where we have to protect the lab from us. We've just walked through a dusty mine drift. We have to get that dust off. That dust is loaded with naturally occurring uranium and thorium, and that stuff cannot get on our sensitive instrumentation. So we wash our boots, we take off our clothes, we shower to get the dust off behind the ears, just like your mom taught you. Got to wash behind your ears. All that training actually comes in handy here. We provide you with clean room garb. The laboratory itself is operated as a Class 2000 science grade clean room. The whole thing, all 5,000 square meters of the laboratory space underground. Grab a cup of coffee in the kitchen and dining area, and then you don your safety equipment, which is hard hat and safety glasses, and you can formally enter the clean lab itself. And this is what it looks like. It looks like an industrial site underground. Those once were dirty mine tunnels, but then they were coated with concrete, sprayed with shotcrete, hand troweled, and painted to create a barrier to keep things from penetrating through. Every nut, bolt, screw, battery, every computer that comes in is hand cleaned by a cleaning staff. Not a single thing that you see anywhere in these pictures did not go through a individualized cleaning process before being brought into SNOLAB. We can't have that dust getting into the laboratory environment. In fact, some places are so clean you have to take a second air shower just to go into them to get any extra particulates off of your clothing, and you're already in a clean room environment. We have lots of underground facilities. We make ultra pure water, we make liquid nitrogen, and these are just pictures of some of the facilities we have underground in this space. We have people here wiring up hardware for installing quantum sensors inside of one of the experiments in the lab. We have a life science lab. We can do chemistry and biology experiments underground as well. So this is what the lab layout looks like. When we entered to take showers, we entered in over here. This is the old space here. This is where the original Nobel Prize winning Sudbury Neutrino Observatory was and still is located. It's now been upgraded to something called SNO+. But that lab space was expanded and then formally opened as SNOLAB around 2012. And now this is the 5,000 square meters of lab space. The SNO cavern is still the largest cavern. It's about 30 meters high. I'll have a picture in a moment. But we have other spaces that are large cavernous spaces. I'll have a photo of that, that we can also put giant experiments in as needed. This is a picture inside the cryopit. This is actually the baby of the caves underground where we can put an experiment. And we are intending to host a next generation neutrino experiment in here that will fill out to the walls of the cryopit. So this is looking from the top of the cryopit straight down to the floor where there's a whole bunch of assembly equipment for one of the other experiments in the lab right now. And this is just to give you a sense of what some of the work can look like here. So the two people whose faces you can see here, they are students, they're undergraduate students who work as scientific staff for a term or more than one term to gain experience in doing scientific activities, engineering, physics, and astrophysics. And they are currently working through this glove box on a dark matter experiment. I'll come back to that in a bit, called DEEP. And Pierre here is one of our research scientists who's mentoring those students. Now you might think, oh gosh, he's got a glove box. It must be really dangerous in there. Nope. Nope, the humans are the danger. The glove box is to protect the instrumentation inside from being touched by people. Because even a single fingerprint can doom one of these experiments. Your fingerprints have potassium in them, and that potassium is naturally radioactive. and that can doom an experiment in SNOLAB. So it's protecting the instruments from us. This is a schematic of the Sudbury Neutrino Observatory, or SNO, and this is an interior shot with all of its liquids in place. It is a liquid-based detector for detecting neutrinos. It is housed in a 30-meter tall rock cavity. This acrylic sphere you see here is 4 stories across, and it's filled with the target liquid where the neutrinos will interact. And it's managed by an international collaboration of about 100 people from North America and Europe and Asia. Now, one of the things that SNO Plus and another experiment I'll talk about in a moment want to do is they want to give us an early warning using neutrinos of the next galactic supernova. So this is an animation showing the formation of the Crab Nebula. That started off as a supernova explosion and now is a wild and beautiful expanding nebula. And what we want to do, we learned lessons from the 1980s with neutrino experiments that were running there, that hours before the light from a galactic supernova, neutrinos will arrive at Earth first. And this was the subject of my Hartness House workshop talk. But what we want to do is we want to gang these detectors together globally and make an early warning system so that light-based astronomers know that a supernova is coming. We can give triangulation information on the sky, and we can then use that to tell astronomers, look here, this region is where the supernova is likely to occur. So this is another experiment at SNOLAB. It's a dedicated supernova early warning detector called the Helium and Lead Observatory, or HALO. And as its name implies, it uses helium and lead to do all the work. The green stuff is 79 tons of lead. The silver things, those all contain 128 tubes filled with very precious helium-3. And when neutrinos interact with this, they make pulses of neutrons, and the neutrons get captured in the helium-3. Very few things underground will make pulses of neutrons spread over many seconds. That's the signature of a supernova and not much else. Again, managed by an international collaboration. This one is a much smaller collaboration. There's only about 20 people on this experiment. So everything I've said so far about astronomy without light is still concerned with what physicists call normal matter, atom stuff. Electrons, protons, the things that make up protons, the things that make up neutrons, the cousins of electrons, the cousins of the things that make up protons and neutrons. That's all normal matter. That's stuff we've been studying in the lab for almost 2 centuries at this point. But there is more to the universe than normal matter. And this is really the elephant in the room for astrophysics these days, because it turns out most of the matter in the universe is not the stuff we've been studying for 2 centuries. Most of the matter in the universe is something called dark matter. What is dark matter? Dark matter, as its name implies, is a form of matter that neither absorbs nor emits light. It is the most light-unfriendly thing we know of in the universe. If it wasn't so unfriendly with light, we would have noticed it a long, long time ago, because we're very good at seeing when light is emitted by things or interacts with things. What's interesting about all of this is when we look at the sky on Breezy Hill, we look at the beautiful Milky Way, we look at the stars, we are distracted by those lights. It's natural, we're humans, we're drawn to those lights. But the lessons of the last 30 years especially are that most of what matters in the universe, the reason those lights are where they are, is because of the dark things in between that we not only can't see, but which do not respond to light. Stars and gas in galaxies like Andromeda, like the Milky Way, like all the other galaxies we've been able to do this kind of imaging and astronomy and spectroscopy techniques with, all of the stars and dust in these galaxies are moving way too fast, especially as you get out into the suburbs of the galaxies, to be explained as being held in place in these wildly fast orbits by all the luminous matter that you can see. Even if you add up all the dust that recently there was a breakthrough measurement in the dust between the stars and how much there actually is, and it matches what was expected from other measurements. This is actually really important. But even if you add all that up, the stars and dust in the hinterlands of galaxies are moving way too fast. Something is holding them in place and letting them go that speed. Galaxies in clusters, so groups of galaxies, The galaxies in those groups are also moving way too fast and are bound strongly way too far out from their center of gravity to be explained by being held together only by the normal matter that makes all of these up. If you go and survey the universe on its grandest scales, cosmological scales, using images of galaxies and galaxy clusters far out into space and far back into the past, you reveal this beautiful webwork of structure on cosmological scales. This is observational data from the Sloan Digital Sky Survey. It's quite old data now, and it's expected to be supplanted by next generation instrumentation. And yet, the clumpiness that you see here, you think, oh, that's probably just explained by the fact that the galaxies are in there holding stuff together. But that clumpiness at this stage of a universe that's 13 billion years old, it's too clumpy. It's way too clumpy. This kind of tight web work of matter was not the work of normal matter. Something else shaped this early and fast in the universe. And in fact, we can look at light that's left over from very close to the beginning of time, the so-called cosmic microwave background, which dates from just 380,000 years after the Big Bang, shows us hot and cold spots spread over the sky that are way too hot and way too cold, indicating the amount of matter that was clumping in them to be explained by normal matter doing that early in the universe. There's something else out there, and all of these lines of evidence, which ironically come to us from looking at different kinds of light, tell us that something dark is there, but light itself cannot touch it. That is remarkable, and that is the puzzle that we are faced with now as a field and as a species. So the question I want to leave you with here at the end is, can we humans catch dark matter itself? If light will not bounce off of it, if light is not emitted by it, can we catch particles of dark matter and study them? And that's the thing I want to close on. Just like you can detect radiation from cosmic rays using your iPhone by compromising the camera, by preventing light from getting into it, and then letting it be exposed to electrically charged particles from cosmic rays, you can take that same idea and you can try to build a dark matter detector out of it. You can take CCDs, these are very large, okay, so these are much larger than the CCDs in your cameras, and they're much fancier. These are science-grade CCDs that can be cooled down to liquid helium temperatures. That gets rid of all the heat in the camera. That gets rid of something called dark noise. How many of you have taken a picture with your Android or iPhone or whatever in a dark room, and then when you look at the image, you can still see colorful speckles in the image? Yeah. So then people have these arguments about how dark are the darks and how light are the lights and so forth. The true black image is nearly impossible in a room temperature camera because heat makes pixels glow. So we take the heat out to get that background noise out. And then we shield the heck out of this by going 6,800 feet underground, surrounding it in lead and plastic and copper to keep other things from the lab out. And then we wait. It's in the dark, it's shielded, it's deep underground, not much can make it there. And we're now looking for dark matter to strike these things and leave an imprint of themselves. We're doing this with hockey puck-sized crystals of silicon and germanium. These are single crystals. An unbroken crystal structure the size of a hockey puck. They're then cooled down with liquid helium. And when you do that, if anything strikes the crystal, it rings like a perfect bell. And you can actually read that energy out. It's literally reading sound waves out of this. Shield the heck out of it again. Wait for something like dark matter to strike it. This is a picture of the refrigerator that's used to achieve that cooling. And the experiments with the CCDs are called DOMIC and Sensei. The experiment with the hockey pucks is called Super CDMS, or the Super Cryogenic Dark Matter Search. We can liquefy 3.6 tons of argon at negative 303 Fahrenheit and use that as a target for dark matter interactions, again, in a shielded environment. This is the vessel that holds the acrylic vessel that holds the liquid argon. This is an experiment called Deep 3600. Gotta love the pun on that. We can superheat liquid Freon. So you take your typical off-the-shelf refrigerant like Freon, which is now banned as a refrigerant, but you can use it for science. You can then take the Freon and you can put it in a liquid but superheated state. So even the slightest bit of energy striking the liquid Freon will cause it to boil. You can capture photographs of the bubbles. You can capture the sound waves from the bubbles. And only dark matter should penetrate this deep into this target. So this is a picture of the pressure vessel shielded by pure water. Inside the pressure vessel is a glass jar. Inside the glass jar is the Freon target. These are actually really beautiful experiments in addition to being practical. So what is it we're trying to do? We go deep underground to protect our observatories from the cosmic noise of the surface world. We peer into the hearts of stars, and we seek to sense the depths of stars before they can be seen with light, so that astronomers studying the light can see it from beginning to end in a supernova. And we seek to resolve the mystery of dark matter, the thing that light itself cannot touch. And so, refining this poem one more time, up on breezy hill the seeing's fine, the Milky Way, the stars divine, at set of sun and rise of night, I see the faintest, farthest light. Between the stars the dark expands, the things unseen, the shaping hands. I've mastered all the heavens bright, but I must learn to see without light. We live in a new age of astronomy without light. Thank you very much. And I guess I hand this back to the MC now, or somebody, yes.
I'll take it, and if you can just stay here for a moment, let's go into the light a little, into the light. Yes, here, over here, we can stand here, and, yeah. And we would like to present you with a gift on behalf of the Springfield Telescope makers. Thank you so much.
This is too much. Thank you. Thank you so much.
Thank you. And thank you for coming too. Okay, Mario, where did you go?
I probably put him to sleep. Oh, there he is.
There he is. All right, I'm going to hand this back to you, and you can say goodnight to people or give us directions. Yep.
All right.
Okay, thank you.
Not much more to say other than thank you for a fantastic talk, and we really appreciate it. Look forward to hearing a lot more from SNOLAB. Let us know when you find dark matter. Thank you, everyone. It's been a fantastic Stellafane. I hope you enjoyed yourself. We enjoyed having you here. Come back next year. Thank you.